I tell you what, let's get where we can see this top corner here. So you may have to drag or reset your window or something to get that visible. Okay. So on 6 it said reset the range to go from 0 to that's the 1.7. Okay. Use a t-step of 0.01 to get a fairly accurate graph. Okay. So that's what he had. So this is the picture you really ought to have for number 6. Now some of you just had this little line because you didn't get zoomed in enough to kind of see what was going on. Right. So you got to be able to use your window and be able to do some things there to see what the graph is. Find precisely by calculation the value where y stops increasing and starts decreasing. Now, what's y? What's y here? What's that? Yeah, we have an equation for y, but what does y represent? No, not velocity. What's y represent? Vertical position. Vertical position. And x represents horizontal position. So when we say y stops increasing and starts decreasing, we're saying its vertical position stops going up and starts coming down, right? Now what happens, what do we know is true when y stops increasing and then starts decreasing? What do we know is true at that moment? The y velocity is 0, right? Absolutely critical that we understand that, right? That you've got to understand that connection. I mean, that's what we've been doing. I mean, geez, guys, it's local max, right? It's local max. What do we do? If you don't know what to do the derivative set equal to 0, right? Well, now we're fine-tuning that a little bit because we're now broken into both a horizontal and a vertical component. But when we say, when does y stop increasing and start decreasing, that's a local max, right? And so it's when the y derivative, the vertical velocity, when y prime is 0. So when it says find by calculation, right, what you ought to be doing is on your paper there, oops, I'm recording here. On your paper, you ought to be writing y prime equals 0. Now, what is the y prime equation? Somebody help me out here. Y prime, which is, what's the y prime equation? How much? Point. Minus 4 sine 2t. That's y prime. Okay, I'm sorry, I tried to do that. It's what? Plus 0.4, 0.3 plus 4 cosine 2t. Thank you. And we want to know when that equals 0. It says find precisely by calculating. So we want to know y is going to stop going up and start coming down, but it's not going up and down, right? It's going diagonally. But at some point, it stops going up, right? It doesn't stop, but it stops going up, right? It's still going to the right, but it stops going up. Now, it might keep going for a long time. It might stay, right? But I don't think it does. Okay, I think it hits a peak. All right, so now you just get on your calculator and solve it. So Mason, go to the calculator screen. Okay, I want everybody to see this here now. Okay, and so we're going to solve that equation. Maybe you had done it already, but that's fine. It looks like you had done some other work up there. But, okay. Oops. Yeah, got it equals. Got to set it equal to 0. Okay. Now, and then we get this n6 thing. We get pi times n, right? And then so that tells us we should have done what here in our solve? What should we have done? Limited it, right? Let's limit it with the vertical bar outside, okay? And let's go from 0, well, we were going from 0 to 1.7, weren't we? 0 to 1.7 is kind of the t-values we were looking at here in our graph, so that'd be a pretty good time to look in between, okay? And there you go. So there's your answer to number 7. Now, let's check that by tracing, okay? So let's go back to your calculator picture. So 0.823. And now wait, hang on, I'm sorry. I did say, well, go ahead and trace. Go ahead and hit your right arrow. Go ahead and hit your right arrow. And he's going to go to 0.823. And it looks like that's right up there near that peak. Now, I'd like to zoom in on that section. So let's do to our menu, and let's do our zoom box here, okay? And let's do our zoom box, and let's go right up and just do a little box right around that peak right up there. So he grabs that little magnifier just like that. That's perfect right there. And that brings us to that. Now, if he had not reset his t range from 0 to 1.7, because I tried this earlier, it's kind of blocky here, right? It's kind of like little line segments. It's not real smooth. Because when you graph the whole big graph from 0 to 12, it can only break it down so much. And you can't go by like 0.01 for your t-step. It won't let you. You can try to put 0.01 in, and then it'll change it back to like 0.13 or something. Because it can't break down that many points. It's limited by pixels, how many pixels are across the screen. Okay? So, by doing it, by just looking at a piece of it in our setup, we're able to get a nice smoother graph because we can calculate more individual t-values in our graph. Okay, now let's go to trace. So hit escape out of that and go to trace, okay? And now let's just type in like 0.7, or 0.8, I'm sorry, 0.8 would be good. Type in a 0.8. So let's pretend we're just not right on there, okay? And so now we're just traced, so hit the right arrow. Let me see how far. Oh yeah, it's going at 0.9, so it's kind of tough to see, but that's okay. So we're right in there. You can even zoom box this again and just get that section right there. But we're looking at when it stops going up. Now it looks like it stops going up about the same time it stops going to the right, but I think it goes to the right a little longer, and then but it's going back down. So at about 0.8, but at 0.823, that's what's happening. Now, what if we wanted to know when it stopped going to the east? When did it stop going right and start coming back to the left? What would we do? Same thing, but it would be x prime. X prime would equal 0, right? We want to know when the x position stops increasing and starts decreasing. So we want to know when the horizontal velocity is 0, when it quits moving to the right. We would set x prime and set it equal to 0. And the particle never stops in this problem, but what would have to happen for the particle to actually stop moving? It wouldn't actually have to be a sharp point, I don't think. But what would have to happen with those equations? X prime, well, we can do the speed equation, that'd be the same thing. X prime and Y prime would both have to be 0, right? It's got to stop moving up and down, and it's got to stop moving this way. Because anytime it's moving, it's going at least one of those two, right? It's moving either up or down or a combination of both, right? If one of them is 0, then it's only moving in the other direction. If they both have value, then it's moving diagonal. If it's stopped, they both have to be 0, which of course means the speed equation would be 0, because here is the speed equation. Now you need to know all three of these equations. Okay, you need to know all three of these. Well, that's not really an equation. You need to know the slope equation, and you need to know the speed equation. You've got to know those. You've got to know those. We're going to do an example here in just a second. All right, let's go on to number 8. It says, well, I just answered, I think. Is he stopped or is he still moving at 0.823? Go back to your, yeah. Is he stopped or still moving? How can you tell? Justify your answer. What would you have to do for a justification of that? Joe, what would you have to do for a justification that he's still moving? I think, hey, hold that thought. I don't think you can justify it by the graph. I know what you're saying. You're saying at that point, he's still moving to the right. Well, no, the path is still going to the right. You know what I mean? But is he moving on the path? It's possible that a particle, it's like Jake said, a sharp point. It wouldn't necessarily be a sharp point when he stops. He could be going on the path, stop, and then start going again. You could have equations that would do that. You see what I mean? So just looking at the path, I don't think you can tell. Ryan, what were you going to say? That's exactly what you would have to do. You would have to put this value, and I would put more decimals than that. Let's do it. So and Mason do it too, and I'll get to that in a minute. Absolutely, this is what you'd have to do. We just got done saying that if he's not moving, x prime and y prime would both have to be 0. His horizontal vertical velocity would both have to be 0. So to show that he's not stopped, you got to show that they're not both 0. Now we know y prime is 0 because we just solved it. At 0.823, we know y prime is 0. We need to see what his horizontal movement is at 0.823. So there's a lot of equations to be solved, equations to remember, and equations to plug into. And you're not going to just memorize what equation to use. You got to understand it. You got to understand what each equation represents, and you got to understand what the values are, what the variables are, or you're just going to be lost. You're not going to have any idea what to plug into. You got to know what they are, and that goes back to this page right here. You got to know what these things represent. Okay? All right, what do you get here, Mason? Do you do it on the calculators? Oh, I'm sorry, I thought you were doing it. Take your x prime, and let's plug in that value. Here's what I would do. I would just type x prime. What's x prime? It was 0.4 cosine t. I would just type 0.4 cosine t. And then, what was it? Minus 0.4 t times sine t. Was that it? I'm just doing it in my head here real quick. Now, you got to put a time sign. Go back here. You got to put it. See how that went to italics there? It thinks that's one word, T-S-I-N, right? It doesn't know that you meant T times sine there. So you've got to put a time sign in between there. So when you see that happen, okay, now put your vertical bar. This is a great, quick way to plug something in. And now we can just go grab that because we're going to do vertical bar. So what we're saying, remember, is with. The vertical bar is with this thing. So we want this expression with t equals that. And it'll plug that t right in there for us. Okay, hit enter. Okay, there you go. Now, tell me what that says. What does that tell me about Adam the ant here? Still moving. What direction? Why? Well, horizontally for sure, but which way horizontally? East. Why? Because it's positive. His horizontal position's increasing. Think of the chart. X prime is positive, so X is increasing. So he's going right. How fast? Not very fast. Look how small that number is. It's almost 0. So he is about to turn around, isn't he? Okay, he stopped going up, and we can tell by the graph. He was at a kind of a turnaround point. He stopped going up. He went right just a little while longer, and then he's turning back around. So he's about to stop going horizontally, too. Okay? So there's a lot of information in these values we're finding about the motion of this particle with this parametric equation. All right. And then it says use the zoom box feature to go in on that point, and we were kind of already there. Okay? And so we can kind of see that he was moving there. Okay? At 0.823, he's still got to move. He's still moving right. looks like you got a little farther to go. All right, now I'm going to give you a chance here to work with a partner here or whatever, or on your own. I want you to get into your calculator. You can graph this, probably a good idea. I want you to graph this because I really have a sense that we're not very comfortable, everybody, with what's going on, or else you're just really quiet. And that could be part of it too. But all right, here's a parametric equation. I want you to graph this. Let's use a window of -5 to 5 for the x. Let's use -5 to 0 for the y. And let's have our t go, I don't know, let's go 0 to 5, something like that. So let's graph that. Okay, so everybody do that. Okay, I want you to get that graphed. I want you to find the horizontal velocity at t equals 2. I want you to find the vertical velocity at t equals 2. I want you to find the slope of the path at t equals 2. And I want you to find the speed of the object at t equals 2. Okay, so this is simply doing the mechanics of the formulas on this previous page, right? Being able to just do this, do this, do this, right? So horizontal velocity and vertical velocity are simply the derivatives of x and y, right? X and y are the horizontal position and the vertical position. So the derivatives are the rate of change of their position. So that's velocity. And then acceleration would be the derivative again, right? And so let's talk just about that first. Okay? So what did you get for the horizontal velocity? Negative 11 something? And the vertical velocity? 2 point something. Okay. So if I look on the calculator, this is my calculator up on the screen now. Okay. Is this a picture you got? You get some kind of interesting things with these parametric equations, right? Because you can separate out the x and y movement. Now, if I trace to the right, now when I trace, mine's going by 0.1. Is yours doing that too? It's nice if it is. I think I just have it on automatic. I just did those settings I told you. Now, one of the things I want you to do on our next quiz is I'll give you a thing like that, and I'll say sketch the graph and mark the direction of travel. So here you would mark some arrows. Now this one actually goes and then turns around and comes back. So as I go, I'm hitting my right arrow key. So as my time increases, this is going up and to the left and then back down and to the right. And then you get down here and it actually turns around and comes back. And at 2, it's right there. Now what direction is it moving? North, west, left, and up. It's moving left and up. Now, I don't need the graph to know that. And that's maybe a question I would ask you. I might do this on a no calculator question. I might just ask you, here's a parametric equation, and x prime is equal to negative 11.872. What does that tell you? But right here, this negative 11, this negative tells you what? This is the x prime. So this tells you it's moving left, right? The fact that this is negative. So, okay, so this little assignment I just gave you was just about the mechanics using your calculator to do those 3 things you have to be able to do. Just find those values. But now, the more important thing with all that is now understanding what they mean, what they represent, so that you can answer meaningful questions, so you'll know what to do with them. You'll know which one to use and what to do with it and so forth. So, I take x prime, and what I did is I just typed in my x prime, typed in my y prime, and then I wanted to plug values in, so I just did the vertical bar with a 2. Now, I could have put a 2 right in there for the t. That would have been fine. I could have done sine of 8, and done that. But I get this. That tells me that particle's moving to the left. And this positive tells me it's doing what? That's up, because this is the y prime. So therefore, y prime positive means y is increasing, so it's moving up. So I knew it was moving left and up with those 2 things. Okay, now let's talk about slope of the path. What's the slope of the path right where he is right now? It's negative, slightly negative, not real steep. But it's negative. Now, I know he's going this way. I don't care which way he's going, right? We're just talking about the path. Earlier, he was going this way on the path. Now he's coming back. But the slope of the path doesn't have anything to do with the movement. Notice the t's divide out of it. If you look at our formula up here, the t's are not even a part of it. It's y prime over x prime. dy dt over dx dt, you see the dt's cancel, we get dy over dx. We get the rate of change of y with respect to x. The t's are not a part of it. This doesn't have anything to do with speed, how fast he's moving. There could be nobody on the path, right? It's just the slope of the path. All right. So that is, I got this, negative 0.242. Again, not very steep, and it's negative. Notice what I did. I just divided my y prime divided by my x prime. Right? That's the formula for slope of the path. Y prime divided by x prime. Okay? And that's the value I got. And then finally, the speed. What is the speed of the particle? Now that's actually how fast he's traveling diagonally. How fast is he actually going on the path? That's different than horizontal and vertical velocity. That's horizontal movement and vertical movement. This is those speeds combined. Okay? And what'd you get there? 12 point something. And that's simply the square root of x prime squared plus y prime squared. So I just took my x prime value and my y prime value, I squared each of those, I added them together, and it's just Pythagorean theorem is all it is. It's not hypotenuse. 12 point something. Now that's pretty close to what other value we got. That's pretty close to the 11, right? Wasn't that a speed? Wasn't 11 a speed? A velocity? What velocity was the negative 11? The horizontal velocity. Why do you suppose his horizontal velocity came out pretty close to his actual speed? What's that? He's mostly going horizontally, right? He's mostly going horizontally. He's not going up very much. His horizontal velocity, or his vertical velocity, was not very much. His horizontal velocity was more. And so therefore his actual speed is mostly in the horizontal direction, but he's got a little bit of vertical speed. So that's why his actual speed was more than either one of the other two, but it's closer to his horizontal speed because he's mostly doing that. If you look at the formula, it kind of makes sense. If you didn't have any horizontal speed, think about what you'd have. If there was no horizontal speed, you'd simply have the vertical speed squared and then the square root. Right? Well, the square root of the vertical speed squared would just be the vertical speed. His speed would be his vertical velocity, except it'd be positive, right? Because speed is positive. Yes? This will always be positive. Anytime we do square root of something, it's just positive, right? It's not like solving an equation, so there's no plus or minus, right? Speed is always a positive value. Speed is always a positive value, okay? But if you go back to this formula and you think about that, if one of these is 0, right? If he's only moving in one direction, then we got square root of y prime squared. That's just y prime. His speed would actually be the velocity in that direction, except it'd be positive. So that makes sense. That makes sense. Okay? What would happen then? All right. So these are the key things we need with parametric equations in working out some problems. Now, there's some other things we want to be able to do with parametric equations we're going to talk about right now, but those are the main considerations. All right. So let's get your note, if you don't have your notes out already, I guess. Let's go through. Here's a problem I want to talk about a little bit. I don't know that you need to write this down, though. I'm not sure there's anything to write down about this one right here. So I want to bring up a packet that we had a while back called the motion packet, and we worked a problem on that motion packet. It was this problem right here, so don't worry about getting that out or anything. Just follow with me briefly here. It says one way to determine the total distance traveled is to find the absolute value of all the resting points. So here's a position. Now I want you to look at that. This is a particle traveling along on the x-axis. Okay, that's what this problem is. We've done many of those. Wow. We've done many of those kinds of problems. You got the x-axis, we got particle just kind of moving back and forth on here. Here's his equation. Now, I want you to think about this in terms of Adam the ant. If Adam the ant is only moving back and forth horizontally on the x-axis, then wouldn't this be his x position? And what would his y position be? 0. Wouldn't his y position be 0 all the time if he's on the x-axis? He never goes up or down. So wouldn't this really be kind of a parametric equation? Wouldn't this really be the parametric equation for that? Right? And so we could go into our calculator in parametric mode, and we can put this, and then trace, and all we would see is we would see our thing just going back and forth, right, on the x-axis. All right. Now, if I wanted to actually graph that as a distance versus time situation, since it's only one-dimensional motion, okay, this is the graph. And so I went ahead and done it already. And I graphed this as a cubic, and it looks like this. Now, this is his x position versus time. So x is the output, t is the input. All right. If I was actually going to graph it on a y, you know, it would just be this. It would just be going back and forth along here, right? If I was actually going to graph this as a parametric equation. So if we wanted to know the total distance traveled, right, we would do it like we did when we did that packet. But I just wanted to show you that kind of that connection to two-dimensional motion versus just the one-dimensional that we've been talking about. Okay? So that's one thing. There's our adamant problem. This one I don't think we need to worry about. Just, yeah, let's see. What did I have next? We're doing that. We're doing that. Yeah. Okay. Let's do this next. Okay. So now in your notes, go ahead and write this down right here. I got two different equations. Now this is going to be similar to some stuff we did yesterday. Okay, so one of the things we have to do with parametric equations for our next quiz is we have to be able to graph them, we need to be able to trace on them, we need to be able to do velocities and speed and slope of the path, right? And we need to be able to do some of those kinds of things. We're going to do a kind of a story problem situation here in a little bit at the end and be able to use those. Okay, there's a couple other things we have to be able to do. We have to be able to eliminate the parameter. Okay? Eliminate the parameter. In other words, we want to, the parameter is the t. Okay? Eliminate the parameter, which means let's put it in, in terms of just y's and x's. Yesterday we had an example where we got the sine graph. We did an example where when we graphed it, it was just the sine graph. We said, oh yeah, it kind of makes sense. Look at this one here and tell me what you think that graph is going to be. Why a parabola, Chris? So one way to do this is simply with substitution. The very simplest ones are substitution. Since x is equal to t, okay? Since x is equal to t, we're going to take that there, and we're just going to substitute, right? Since x is equal to t, we're just going to substitute that x in for that t, and we're going to get y equals x squared. And that's exactly what you would be looking at. You would be looking, if you graph this, you'd be looking at a parabola. Now the particle would be moving along on that, and I think there's a picture of this one in your book somewhere where they have the parabola. Yeah, at the bottom of page 244, and we'll get into that here in a little bit. But they have a picture of this scenario that we're talking about here. Okay, now, let's move over to this one. What about this situation? It's not quite as easy to just do a straight substitution because we got t cubed, but if you think about powers and stuff like that, what substitution could you make here? What's another way to think of t to the 6th power? Isn't that t cubed squared? Isn't it? T to the 6th power, power on a power, you multiply the powers. So what would be another way to write y equals t to the 6th? y equals x squared, because t cubed is the same as x. T cubed, that's what x is. X is equal to t cubed. So you got to be a little more creative there. But x is equal to t cubed, and y is just that squared. So these two parametric equations would have exactly the same graphs. Oops. But if I look on page 244, we can see, and we did this yesterday with that sine graph, we can see that the particle is at different positions on there, okay? So at t equals 1 or at 0.75 or at wherever, the particle is at different places on there. The movement is different. Same path, different movement, okay? All right. So that's something that you may be asked to do. Here's a parametric equation. Eliminate the parameter and write y in terms of x. Now the other option you have, besides substitution, is you could solve one of them. What you basically have is two equations, like a system of equations. So I could have done it this way. If I can't quite see that, I could have done this. I could have said, okay, x is equal to t cubed, so I could solve this one for t. And so this would be cube root of x. I could do the cube root on both sides, which I know is x to the 1/3. So I could solve one of them for t, and then make that substitution back into there. So if I get t is equal to x to the 1/3, then I could move that into there. So now I would have y equals, and now take out the t, and so I would have x to the 1/3, and then to the 6th. And then power on a power, I multiply 6 times 1/3, I get y equals x squared. So if I'm not quite creative enough to see that substitution there, you can just solve the x equation for t and then substitute it into the other. Okay? We often do that with linear situations. You're going to have some in your homework that look like this. 2 plus 3t and y equals 7 minus 4t or something like that. That's your parametric equation. If you want to eliminate the t, if you want to see what this graph would look like as a y in terms of x equation, take your top one, subtract 2, divide by 3, you get t equals x minus 2 over 3, and then substitute that back in there. And so you get y equals 7 minus 4 times that, right? Now it's just some algebra. So you could multiply the 4 through there, so that'd be what, 4/3 basically times x minus 2, you know, and then finish that out, right? Distribute it. You bring that 3 out there and do 4/3, whatever. Distribute and just a little bit of algebra. So now you could get y in terms of x. Okay, and you can see it's going to be a line, right? It's going to end up being a line. Okay, so that's another thing we want to be able to do with some parametric equations, is be able to tell what the equation is with y in terms of x. All right, the last thing. Oh, one other comment I wanted to make. Yeah, let's look at this. Write this down. This is the last thing, and then we've got a story problem to do, and then we'll have homework time. Parametrics can be useful for inverse functions too. Parametrics can be useful in inverse functions, because what did we say? If you wanted to do an inverse, what is one of the most important properties of inverse functions? Of a function and its inverse. What is the difference between the two? You switch what are they? You interchange the x and the y. Well, this is a beautiful thing with parametric equations, because a parametric equation, you have a separate equation for x and y. So how easy is it to interchange the x and the y? It's as easy as that right there. Right? Because think about this now. We just got in talking about, what is this, what graph is this right here? Y equals sine x, right? X equals t. Substitute the x in for the t, right? This parametric equation is the equation y equals sine x. So if we interchange the x and the y, what's this one got to be? Inverse sine, arc sine. That's got to be arc sine. And it is. I don't want to take time because I want to give you some work time here. But this is arc sine. That easy to do arc sine, the inverse function. So if I wanted to do the inverse function of any kind of an equation, say I want to do the inverse of, I wanted to graph the inverse of y equals 3x cubed minus 7x plus 2. And you might, well, in algebra class, you'd say, well, interchange the x and the y and then solve for y. Well, the problem is if you interchange the x and the y here and then try to solve for y, you can't. You can't. But with parametrics, it's this easy. Just let x equal t, let y equal 3t cubed minus 2t plus 2, right? Isn't that the same as that right there? Isn't that the parametric version of that, right? So what's the inverse? Flip it. So the inverse of this function would be x equals 3t cubed minus 2t plus 2, and it would be y equals t. That would be the inverse. That would be the inverse graph of that right there. So parametric equations can be really useful. Now we won't use them that much for that, but just an interesting thing about parametric equations with these inverse functions. I don't think there'll be anything on the homework with that or that you'll have to do in the quiz. Okay, but I wanted you to just kind of see that. Okay? All right. So anyway, getting the parameter by itself is something we're going to have on the homework and something we want to do. All right, the last problem we're going to look at, I think for right now, we're going to skip number 11. Yeah, we'll... Yeah, we're going to skip 11 and 12 because we talked about those a little bit. They're ellipses, so we're going to let's not mess with that. Okay, we're going to do. This is problem number or example number 10 in your book, and one of your homework questions relates to this. So if you would turn in your books to page 247, 247. So we're going to work through this example 10, and one of your homework questions, or a couple of your homework questions actually at the end, relate back to this problem. So this will give you a good blueprint for how to attack those problems. All right, example 10 on page 247 says a major league fastball leaves a pitcher's hand traveling horizontally with an initial speed of 150 feet per second and an initial height of 7 feet. Ignoring wind resistance, and then they have a little comment there about how major league batters don't ignore wind resistance. But anyway, ignoring wind resistance, describe the ball's trajectory. When and at what speed does the ball cross the plate, which is 60 feet 6 inches away, 60.5 feet away? Is the pitch a strike? If the batter, the catcher, and the umpire all miss the ball, where will it land? Okay, so this is a situation, realistic situation, except ignoring wind resistance. He's going to actually throw it perfectly horizontal. That's just going to make the problem easier for us, okay? Probably not the way a pitcher really releases the ball, but just to make it easy, you're going to release it horizontally. Now, it's going to drop due to gravity, right? It's going to drop due to gravity, all right? But he's going to release it horizontally. So we want to know if it's a strike. We want to know how high it is, obviously off the ground when it gets to the plate to tell if it's a strike. We want to tell where it lands. I think it might even say how fast is it going. Did it want to know that? Yeah, what speed does it cross the plate? All that stuff. Okay, so, well, what do we need? We need equations. We need an equation for the movement of the ball. We need a parametric equation for the movement of the ball. Now, let's talk about horizontally first. Horizontally, the ball is going to move at 150 feet every second. So t would be the seconds. So how many feet would it travel? What would be the equation for that? 150 times t, right? We'll call this 0. We'll call this 0 right here, okay? So if we had an axis to put in here, if we had an xy axis, right, this would be our origin. So this would be, it's going to release its hand 7 feet, right? It's going to release up here, so about 7 feet. Plus you got the height of the mound too, right? So 7 feet off the ground is where he's going to release from. So wouldn't that be the horizontal position of the ball, right? After 1 second, it would have went 150 feet. After 2 seconds, it would have went 3,300 feet, right? Because it's not slowing down because of what? No wind resistance, we said, right? No air resistance. So horizontally, it's moving on. When he releases 150 feet per second, it's going to keep going 150 feet per second, right? Because of no wind resistance. Horizontally, that is. Now, we know it's dropping, but horizontally, it's still going to have that speed. The only thing that would slow it down in its horizontal motion is the wind resistance. And we said we're ignoring it. Okay, what about the position of the ball? The y equation. What's the starting position of it? 7. Okay, now here it gets a little trickier because probably to get this one, and I would give this to you in a problem, quite honestly. So I don't want to spend a lot of time coming up with it. But it really comes from this. What's happening to the ball is it's being pulled down by gravity, which is negative 32 feet per second, right? And that's acceleration. So that's y double prime, right? Y double prime is acceleration, and in this case, that's the vertical acceleration. That's what's happening to the ball, okay? Well, if that's y double prime, what's y prime? Negative 32t plus some constant. Now, how can we find that constant? Well, at time 0, right when he releases it, this would be velocity, right? Y prime would be vertical velocity. What's the vertical velocity right when he releases it? The vertical velocity. 0. It's not moving down at all, right? Right when he releases it, it's only horizontal. So at time 0, this should be 0. So what's c? 0. Okay, so c is 0. So we can ignore it. So what would y be then? Remember what to do here? That's t to the first. Negative 16 t squared. Well, it's going to be plus 7, right? Plus some c. Well, what would c be? Well, at time 0, what's the y, which is vertical position, right? What's the ball's vertical position at time 0? It is 7, right? So this would be 0 plus what would make 7. So the c would be 7. So this equation, I'll just write it this way since I already have the 7 there. So that's how we could generate the y equation in this problem. But I would probably give it to you, but it's easy. It just starts with acceleration, gravity, and it's just a couple of antiderivatives with a few initial conditions thrown in. Okay? So that is the y position of the ball, and it's easy, right? And that is the x position of the ball. Okay? The x position of the ball. All right, so there's our initial condition. So there's our parametric equation. So if we graph this with the proper window and so forth, we would see something that looks like the picture I have here in blue. Okay, we would see the movement of the ball. All right, so we could trace and stuff like that, but I don't want to do that. You need to actually do the calculation. So let's do the first calculation. They wanted to know what was the speed when it crossed the plate. How fast was it going when it got across the plate? So what do we need to do? We have an equation for speed of a parametric thing? We do, don't we? What's the equation for speed? X prime, what's x prime? 150. Oh, we don't even have to plug a t into that, right? That's easy. Right? Plus y prime. What's y prime? right? Isn't that the speed equation? Well, we can't, what do we need? We need t. What t do we need? Well, no, I mean, t is a time. I mean, but what time are we looking for here? We need to know when it crossed the plate, right? We want to know the speed when it was across the plate, so we use this equation where we need a t to plug in when we need to know when it crossed the plate. Okay, so we got to figure that out. This is what I was talking about earlier. All we're doing is using those three equations that we talked, those three ideas we talked about at the beginning of the day. But you got to know what they represent to know what to plug in, to where, and what equation to use. How are we going to figure out when it crossed the plate? What about the 60.5? Where do you put the 60.5 in? You're exactly right. Perfect. It would be for x, right? X is the horizontal position. We said this is 0 here. The plate is when x is 60.5. Perfect. There's only so many places you can plug in, right? We're looking for t. We've only got two equations. It's got to be x or y, right? I mean, there's not that, you don't have that many choices. So what we need to do is solve the equation 60.5 equals 150 t. So we put a 60.5 in for x. So what do you get? What's 60.5 divided by 150? How much? 0.403, whatever. Probably should save a few decimal places, but something like that. So we need to put our 0.403, right? We need to put that in there for t. Probably should use a few more decimal places than just that. Okay? So go ahead and do that on your calculator for me. What do we get? 150.55. That's weird. It's going faster when it crossed the plate than when he released it? Oh yeah, and there's no wind resistance, right? There's nothing slowing it down horizontally, and gravity's pulling it, so that's speeding it up as it goes down. So it's still going 150 this way and gravity, so that's why it's kind of silly to ignore wind resistance. But that, one of your homework problems, you won't ignore wind resistance, and they'll give you the equation to use. Okay? So it kind of makes sense that it's actually going faster. Not a lot faster, because it gets there really quick, less than half a second. So it doesn't have a lot of time to speed up as it goes down. Okay, is it a strike? Is it a strike? What do we need to know? We need to know how high it is off the ground when it gets to the plate. We need to know what y is. So how would we find y? What do we put in for t? Right? You got to know what these numbers mean. 0.403 is the time when it crossed the plate, so we put that time into that equation, and that will tell us what y is, okay? And so, what do we get? What do you get? How much? Yeah. How much? 4.401. So 4.5 feet. Seems a little high. Depends how tall the person is, right? Right, John? Yeah. I mean, to really answer that question, you have to know the strike rate. Right? You have to know what the heights are. but it could be a high strike. But that's how. But you got to understand what these things are, right? Don't worry about how I came up with that. Now, you're going to get another problem in your homework with this similar situation. I think they changed the initial velocity. If they don't change the height he throws it, this is the height he throws it. This is the just gravity, so that's not going to change. That kind of thing. But that's how we can use those equations to answer questions in this situation. But you got to understand what those different things represent. Then I think the last thing was when will it? How far will it travel till it hits the ground or something? Yeah, where does it land? So what would you do for that? Put a 0 in for y, because when it hits the ground, it doesn't have a y value. The y is 0. So you put a 0 in for y, find out what time that is. But that's not what they wanted. They didn't want to know when it hit the ground. Where did it hit the ground? So find when it hit the ground, put that time up into this equation, and that would give you your x, which would be what the x value was, how far it was horizontally when it hit the ground. Okay? So, just using that equation to answer all those different questions, just knowing what those things represent is important. All right, so your homework sheet, you had the 4.4 questions. I'm going to take a couple things off of that, and then you can use the rest of the time to work here. So, if you look at 4.4, let's take off 11 and 12. Okay, let's take off 11 and 12 here. Okay, and so you have some early questions which are just some simple parametrics. Some of them they want you to just graph and trace and that kind of thing. A few of them they want you to eliminate the parameter, solve for t and substitute and get it y in terms of x like we did on a few. And then some of these questions at the end are kind of like the baseball one, right? Using this, talking about this, finding the speed and those kind of things. All right, so 4.4. You want to do a couple more. Now, some people did more than they needed to. I mean, the other class actually came in. But in that packet, right, we did the first 28. There was only 18 problems, but that first section of multiple choice. Then there's another section of multiple choice. That's where I wanted you to do a handful, 2 or 3 in that section, right? Some people did all those and then got into the response too, which is more than you do. Okay, there's not very many in that next section. I think there's only about 7 or 8 that are circled, right? So you can keep doing a few there, but don't worry too much about it. But by the end of the week, we want to get through the multiple choice ones in that packet. We want to get through the multiple choice ones. All right, go ahead and go to work on 4.4 homework. Make sure you're on the right line now. We've kind of skipped around here a little bit, so it's 4.4.